Hello, this is my explanation for the code of the optimized jump rope program. So, this program is very long. It's 350 lines almost, but most of the sections have some sort of like repetition or some like easily generalizable purpose. So this shouldn't be too long of a video. So assuming you've already seen how the behavior of the project works, hopefully you can figure out what most of these variables do. So these are the libraries. Yeah, you need wire to use VL53LOX, the sensor, and then you fast LED for the lights. And then I have a pitches file, and what that does is I can for the when health is on and you run out of health and you play a song, it's like very easy to play notes rather than having to type a certain number for the frequency you want of the note and having to search that up. You can just type the note name. So for example, like G2 is just note underscore G2. Okay, so going back up, so these are just the objects. All right, remember these names. So LEDs is the light strip, and sensor is the distance sensor. And then with these, so with these two lines right here, you can basically extrapolate how the circuit should work. You have buzzer on pin 9, and then you have potentiometers that are read from analog 0, 1, and 2. To read from a potentiometer, you want to put your you want to connect your analog pin to the center pin of the potentiometer in almost every case I've seen so far. And then the other two pins of the potentiometer are just positive and negative. Yeah, it should be very easy to search up online how to perform this analog read to find the value of a potentiometer. Okay, and then I have these. So this section of variables is the time intervals in which we wait for checking or changing certain actions. So this is buzzer duration. So you'll turn on a tone for the buzzer on buzzer 9, and then you'll turn it off after 400 milliseconds. You can just change these if you want. Tick pot change rate is how often we're checking the tick pot to see if we should change the ticks. Like constantly scanning these is probably irrelevant and doesn't matter because you probably aren't changing the tick pot every fifth of a second. Why would you do that? So yeah, you can have even a slower rate. I just kept a rate that's like pretty lenient and nice so that it's not too delayed, but also gives you plenty of freedom to not slow down your system by constantly checking for this tick pot rate when it probably won't change that often. Flag update checks for many of the other changes. So flag update occurs every 300 milliseconds, so 3 times a second, and that's basically has to do with this flag updater method, and it checks your tick pot chunk and width, and those are all like pots. So you want to check those to see if you need to change the configuration of the lighting. Okay, and then these are all basically the last time that the some condition was updated. So you'll see these are very important for multitasking. So I'll get into that later. But you need some variables equal to 0. So these speed variables are if you change the tick rate. It's, let's say you're jumping, you can potentially shake the potentiometer and it might make the speed like ripple. Like it may not be a big ripple, but if the speed is rippling, we don't want that. So I divided the potentiometer values into 5 distinct values or sections. So it's like not as sensitive. And so you can change these to whatever. Basically what it is every time this amount of milliseconds passes, all the lights on the LED shift by 1 unit. So yeah, and so there's a max speed of around 5 milliseconds. I cannot find a way to shift things faster than 5 milliseconds. So yeah, I mean you can try, you won't break anything, but It's also like kind of unjumpable, anything higher than 5 milliseconds, unless you have like a single light or something. And then another thing is that the sensor, the light sensor, is actually capped out at a 20 millisecond sensing interval, so it can only do one measurement every 20 milliseconds. So what this means is if you have a wide width of lights and you're passing through the reference light, that green light, and this incrementing speed is faster than 20, then you'll actually slow down when the light passes through, because the Arduino needs to slow everything down so that the sensor can scan every single time the red light crosses the reference point. So yeah, so if you want to go below 20 milliseconds, it's possible you will get a slowdown, but if you use a very low width, the human eye cannot tell that the speed is changing or slowing down. So yeah, if you want a high speed for your jump rate, you can do that, but you need narrow width, or you're gonna get really annoying movement. Okay, so next is the entire health system, which is actually a little more complicated than I thought it was going to be. So, so your first variable is health on, and what that does is if you turn health off, then you'll have infinite health, and your reference light will always be red, and when you miss the jump, it will buzz. When health on is true, that is when the gradient reference light occurs, when the light starts shifting down to yellow, and when you lose, you get the song. Okay, so yeah, and then you can always change the starting health to whatever you want. So the way this starting health works is that so the way we calculate the way the light changes is based on the starting health, as well as the high hue and the low hue and the critical hue. So what we do is we create basically an array, and this array has the size of the starting health. Now we fill this array with values that linearly change between the high hue and the low hue. So the lowest, so the first index of the array, and this array is called hue. The first index, which is hue 0, will be equal to the high hue, and then each preceding value will go linearly approaching to 45 until the last value of the array. So the first value is 127 and the last value is 45. Oh wait, actually no, it's the other way around. The last value is 127 and one of the first is 45. It's not the first, it's actually the second, because I wanted to put a critical value to indicate to the player when they have 1 health left. So that's critical hue. So that's the only like break from the pattern. So in the video, you'll probably see that it starts at around cyan, the health, ends at around yellow, and then when there's 1 health left, it'll go to pink. And then dead hue is when it's not really relevant, but dead hue is like when you die, it changes into this color, which is red, but it doesn't matter because the light will play and then the gradient will occur. So this line is kind of irrelevant. But in case you somehow wanted to cut out the song and just have a dead hue, you can do that too. Okay. And then, yeah, so this hue starting health is the representation of all the values you calculate, and you'll see the equation later. You can also look on my blog post for more detail on that stuff. Okay, reference position set to 0. I actually haven't tried changing the reference position, but I think it should theoretically change, because I think I have the code that can handle changing this reference position. So if you don't like the green light being close to the wires, you can change that. These are the initial tick rates. It doesn't matter what this tick rate is because it gets immediately updated with the tick pot change rate. But if you have tick value as really low to begin, then the light will like rush super quick and then update immediately to the pot thing, but you'll still see it at the speed that it starts. So I'd rather have it pretty slow, so I put it at 100. And yeah, and these are initial like conditions. These don't really matter because they get changed almost instantly. Okay, so minimum space, we'll get into that later. Not really that important. Start is the starting position of the light. I start at LED 20, but you can start at anything. And then we have a flag to check if we need to change the values of the light configuration and restart the cycle of turning the lights. Okay, so here's a setup. Wow, that actually took me a while. Okay, here's a setup though. The setup has it's pretty common sense. I think as long as you've made a couple Arduino programs, you probably know what's going on. I mean, I don't really know what wire is, but you got to begin it to activate it. So there's that, and then this is how you basically make the program aware that the light strip is a WS2812B. So here's the sensor check. So you want to check that the sensor is like functional, and this is how you do it. Basically, you get stuck in this while loop if it fails to detect, like if there's no initialization. I found that this sensor sometimes will just randomly fail when you try to start it up. So, but it doesn't fail like in the middle of the program running, but like I'd say 1 out of 5 times you have to try again and like unplug the Arduino and restart it. Okay, this is a big deal right here, line 74. This changes your maximum speed that you can measure, the rate that you measure, the rate that it's the fastest measurement rate. So this is every 20 milliseconds. So this must be to the 10 to the power of 6 seconds then. Okay, and then yeah, the rest is, this is just printing your starting health, so you can see what your starting health is. And then we have using your starting health, we're generating the array that we use to figure out when you lose health, what color should your health like be, your reference point. All right, next is fast LED set correction in the loop. So we're starting with the loop now. So this is just color correction. I found this color correction to be the nicest, easiest way to make the colors look good in my environment. I don't think this is that relevant. You need millis. What millis does is it tracks how much time has passed since the program has started. You need this for the program to understand when it should check certain conditions to update things or change things. So yeah, this is required basically. And then here, if flag just means if any of the potentiometers have significantly changed, you're gonna reconfigure the lights and then you're gonna turn off the flag. Okay, so here's the first example of multitasking. So basically using millis, you can find the current time. So it takes the current time and it figures out like since the last time that the light has been updated, is it greater than or equal to the tick rate? So if like, let's say tick is 20 milliseconds, basically it's asking, has 20 milliseconds passed since the last time the lights have been updated? And if so, then you're gonna set these both equal to each other so that they don't trigger themselves again until the next 20 milliseconds. And then you're going to shift all the indexes of the LED object. So yeah, and this line 95, line 95, is it line 95? I don't remember. Anyways, anything weird you see here is to keep the green, the reference LED, in the same position, yeah, keep the reference LED in the same position while keeping the rest of the lights moving. Yeah, and then this line right here is because of wrapping, because technically even though the strip looks like it's visually in a circle, it does not wrap on itself. It is still a strip with an index that does not automatically wrap on itself. So a lot of wrapping techniques are used here. Okay, and then you have to so once you change the value of an LED, it does not immediately update. You actually have to show everything. So this shows everything at once. And then you do a check for the buzzer. So like, should the buzzer buzz? And then you check has the have potentiometers moved, or has health changed? And if so, then you reconfigure the lights. So this is what makes the lights like look like they reset back to the start position every time I change the potentiometer, is because of this light config that is triggered off the flag updater. Okay, here's the light config. So the light config needs the chunk amount and the width to function. Yeah, I noticed a lot of these not potentiometers, what am I talking about? A lot of these parameters I don't actually need to pass in. Yeah, I don't know if that's poor practice by me or if the other way is poor practice, but it doesn't matter, and I thought I'd just include them. So, yeah, so what you have to do first is make everything black. But it doesn't show the LEDs, so you won't see that it's black. But the reason why you make it all black is because if you have all these LEDs already showing, and then you fill it with the pattern you want, when the potentiometers have turned, then those patterns both will actually overlay on top of each other and look terrible. So I did that, and I was like, what is going on? So yeah, that's what this fill solid is. So CRGB is just the RGB value. I'm not sure what C stands for, but if all are 0, then it is black. Black means there is no light. So you can use the chunk amount to figure out how many lights, like distinct light chunks, there are turning. So I've made a case statement up to 6. I believe this behavior you can generalize with some type of formula, but I thought it was pretty impractical to go more than 6. Like, just increase the speed. If you increase speed to like 20 milliseconds and then you have a case statement of like 6 and you're going with 6 lights spinning all around, you are gonna have such a hard time jumping. I don't think a human on the planet Earth can jump at the rate that I have with 150 LEDs. So yeah, I'd like to do a little paint description right now of what's going on. So here I have a circle. Actually, okay, so yeah, let me just draw a circle. Okay, and then I'll get back to this later. Okay, so notice how these call different methods, and these methods, they actually call into each other. So NT1 does not, but NT2 calls NT1, NT1 calls NT3 calls NT1, NT4 calls NT2, NT6 calls NT3 and NT2. Yeah, so yeah, and so what is this? Well, they call each other because supposedly, let's say I'm trying to make NT4, which means I need 4 lights traveling around. So if I'm gonna let's see, I'm going to make the lights red. Okay, so I have 4. Sorry, I'm using Microsoft Paint. I have 4 lights like this. Okay, these 4 lights kind of represent the fractions of a circle. So this is like 4 out of 4, this is 1 out of 4, 2 out of 4, 3 out of 4. If I had 2 lights traveling around this circle, I could put them like right here, and the like green. If I had 2 lights, it would be like right here and right here. There's overlapping behaviors for the lights, so I can reuse the code, and it seems to have something to do with the prime factorization and like removing duplicate prime factorization numbers. So, for example, the prime factorization of 6 is 2 and 3. So I just call 2 and 3 and then call whatever I need left. So this is the 1 out of 6 point, and this is the 5 out of 6 point. And then like 4, the prime factorization of 4 is 2 and 2, but that's just duplicates, so I just say NT2 and then I just put these on top of each other. So yeah, and 3 is prime, so you just call 1. It seems like same with 2, you just call 1. Yeah, so there's some, you can probably generalize this. I was thinking about it, but then I was like, actually, this is probably good enough already. So yeah, okay. And then this also takes into account the width. So like if I were to put a light down, if I were, let's say I do like NT1. So this basically, NT1 is 1 point, right? So there's actually a black light at the start point, and then there's a red light that is in front of the it's in front of the black light, and it's traveling. And then this modulo handles if the width is too wide, sometimes some red lights will wrap around the light strip before the loop restarts for the black. So you have to wrap it around, or you'll have a light that's just teleporting when it hits the end of the strip. And then yeah, so this formula, you can take it to any fraction basically. All you have to do is add the num LEDs divided by whatever value you want, like whatever number of dots you want. So if I want 2 light chunks, then I have to put it divided by 2. And then I have to also do this num LEDs because I'm adding onto the start, and the start ends at the num LEDs. So you have to modulo it. And then you just do this over and over again basically for different fractions. It's super easy to generalize. Okay, next is buzzer check. So what I wanted to do is I actually had to make it so I have to check when the light next to the reference position is red, not the reference position, because I want the reference position to always show the light that I want it to show. Like if it's green, I want it to show green. If it's yellow, I want it to show yellow. It should never show a different color. So I have to look at a different position that is near that, the reference position. And the reason why I can't just like flick it really fast is that it's physically impossible to just flick something really fast without you visually being able to see it. Because it turns out that where is it? I lost my spot. Oh yeah. To make CRGB red true, the light literally has to be red. Its value, even if its value is red, the light literally has to be red. So unless I call fast LED show and literally show it, it will not activate, which is a bit of a problem. But I mean, this like incremented by 1 unit is not really a big problem, and I don't really notice it when I'm using the jump rope game. So then I just read a range. If it's less than 700 centimeters or millimeters, which is 70 centimeters, which is about 3 feet, then the tone activates. So if the tone basically senses something nearby, it will activate and buzz. That makes sense, because if you were jumping over the buzzer and the buzzer is like aimed at maybe your shin, like a sideways shot, a side shot of your shin, and you can jump over it, then the sensor should read something very far away, not less than 3 feet away. So then the buzzer activates, and then the health reduction happens if you have health on. And then this is how you turn off the buzzer. Use another multitasking strategy. Here's the flag update. I kind of talked about this before. It uses another multitasking strategy, and then it just checks these different pods. So all these pods use a very similar behavior, and they all go like this. So you start by grabbing a value from your analog read of the port you wanted. So I believe tick pod is analog 0 on the top of my code, and then you'll get a value. And then with that value, you'll figure out the speed. So these numbers aren't perfectly equidistant from each other, but they're good enough. And so you also, when you check the flag, that doesn't necessarily, when you check if the flag should turn on, that doesn't necessarily mean that anything has changed yet. You still have to verify that something changed. So in order to verify that something changed, I have a variable that remembers the last value for the tick speed. And if that tick speed just changed, then the flag becomes true, and the memory gets updated to what just happened if it changes. And then when it changes, the data also gets printed. So only when data changes, only when the flag actually activates and some value that is important changes, then the data will print. And so this is the same for every single other one. So here it's about the same, except I'm changing chunk amount. And here it is also about the same. Changing width amount. I also changed the increments of the widths because I realized that the most variable thing here is the width. Because if you have a really long strip of LEDs, then you might not want even a width of like 12 or a width of 8. In proportion to how long your strip is, you might actually want a really large width, or if your lights are really dense, you might want a really large width. So I have a good amount of widths, but then I realized, like, what if your strip is like just insanely long? What are you gonna do? So I thought, why don't I use a function? So this, not a function, an equation. So what it does is it basically just guarantees to fill up all the possible lights as red for the number of chunks you have, and between each chunk you can specify how much space you want, how many black lights you want. And so that's what that variable on the top is, the minimum space. So you can change this. So you can have a width of so instead of caring about the width, you can actually care about how much time you have between each jump, which I thought was a pretty good idea. So that's what this last one is. And yeah, the rest is pretty simple. So this is the print data. If you want to like pause the video, you can to think about it, but basically it's just printing basic data: the tick rate, the chunks, the width, how much health you have, and your jumps per minute, and your airtime percentage, like how long are you in the air. If you have like beyond a high school level of math knowledge, or even a high school level of math knowledge, you should be able to like intuitively know this is probably not too hard to calculate. So I trust you, if you're watching this video, to understand it if you want to. And then finally is well, not finally, but at the last portion is some health management. So we generate the hue array. There's two, this is only for when you turn health on. So this will activate or will be relevant. So if your health is 1, then your first health will be whatever light you set as you having 1 health, which is the critical hue. In the video, I believe that's magenta. And then hue 0 is the dead hue, which is red, but you never see that. When starting health is 2, I made it by default go to the high range of the hue instead of the low range of the hue. So cyan, and then magenta, and then red. And then for all other situations, you so health of 3 or higher, you're gonna have your highest point of health being the high hue, your lowest, not your lowest, your second lowest health level being the low hue, and your lowest being the critical of you being 1 health. And then the rest of the values are calculated through this for loop. So I'm gonna open up my website to show an image of how I found this formula. This is how I found the formula. Basically, I have max health on this left column. I have the remaining health on this column and what the hue value should be. So I started with easy values, like very low health, and you can see that is mirrored here. Oh, you can see that's mirrored here. Critical health, which is dead hue, which is 0. Yeah, same with 2. And then starting at 3, I figured out you can generalize this behavior. So So I would find an equation. Let me just full screen it. Maybe it's, let me just zoom in so maybe it's easier to see. I found this equation, and basically this equation is equivalent to this equation right here. And here's a visualization of what each color would look like. So yeah, up to 5 for the visualizations. And then this equation is right here. So that's how I got the equation. It's not too complicated if you look at it for a bit. Oh, and if you're not aware, the reason why this array is named hue is because I'm calculating these colors instead of in RGB. I'm calculating them in HSV. So HSV is hue saturation value, and hue basically travels along along a rainbow gradient, as you can see from this visual. So if I just change along the rainbow gradient, it should be pretty easy compared to trying to calculate RGB values to generate some type of gradient, which I don't even know how to do that. So yeah. And then so this is just managing health reduction. If your remaining health is 0, then we're going to make the rainbow pattern, which is done with this code right here. And then we're going to play the song and show the and then show the LEDs so that we can show the rainbow. This method isn't really that relevant. Like, I could have just plopped this line in instead of ref hue update, but I was planning to like do some more stuff in it, but I realized this is all I needed to do, and I just kept it here. And then this is the song. I recognize there are better ways to play a musical song than this that are more flexible and optimized, but Beethoven's Fifth Symphony is way too funny, so I don't anticipate ever needing to change that. So I will just keep the code like this, which is as unoptimized as it gets. But yeah, so that's the code explanation.